So thank you for coming. So in this talk, so the title is Foundational Knowledge for a New Project in 2007, Big Data Project. The idea of this talk is to give you enough knowledge in distributed system to fight against marketing bullshit. You read some marketing materials, and if you understand distributed system, you will know if it is true or wrong, or maybe true, maybe wrong, right? So let me introduce myself. My name is DuyHai Doan. I'm working as technical advocate for DataStack. So DataStack is the company which is distributing the enterprise edition of Apache Cassandra. I'm also working on Apache Zeppelin. So if you have any question about Cassandra or Zeppelin, you can drop me an email here or ping me on Twitter. The agenda of this talk is, in the first part, I will give you some summary of the theories and properties of distributed system. Then we will reuse those ideas in chapter 2, 3, and 4. So distributed system theories. First, when we talk about distributed system, we need to talk about time. There is no absolute time in theory, right? And between different machines, you can have time drift. So you cannot avoid it. Even Google, they have atomic clock synchronized by GPS, but still, they suffer from time drift. Of course, they can limit this time drift to a few tens of milliseconds or 20th milliseconds, but still, it's impossible to have perfectly synchronized clock. So the only thing you have to do is to install NTP on production, right? NTP is a standard right now in Linux. But it is not sufficient. You need to configure it properly. If you know that you need to synchronize the clock between two machines which are separated by an ocean or in two different continents, the configuration is different than if they stay in the same room. We talk about time. We also need to talk about ordering of the operation. So if you have different transactions between different machines, how can you know this transaction happened before or after another transaction? Especially, well, when clock is not 100% reliable. So in fact, you can have two types of ordering. You can have local ordering, where if every of your transactions are executed on a single machine. So you can have this local ordering. But global ordering is really difficult. Or unless you have a giant distributed lock, right? You lock everything, you execute a transaction, you unlock, and the same again for any transaction. But in this case, you lose a lot of performance and latency, of course. So local relative ordering is possible. Global ordering is hard, or you have to pay the price for this. Now, going back about time, since we talk about time and ordering, how can we achieve relative or local ordering? There are some known algorithms. The Lamport clock. Here is the pseudocode. So from the sender side, we have a local time. We increment every time. And this timestamp is sent alongside with the message. From the receiver side, the receiver will just take the maximum of the received timestamp in the message and its own timestamp plus 1. So it means that the receiver time will be always greater than the sender time. And with this simple algorithm, you can ensure partial ordering between a pair of sender-receiver. But still, you don't have a global ordering between all the senders and all the receivers. Or we have also vector clock algorithm. I will not go into details. If you are interested, you can look on Wikipedia on internet to understand all the details of this algorithm. The rough idea is every time I have an event, A, B, or C, I attach with this event a kind of logical time, 1, 2, 3, 4. And then every time I send this event to another machine, I also send it with the logical time. So with vector clock, the receiver can detect that, that there is a synchronization problem, that there is a mismatch, right? But vector clock does not help you to solve the conflict. It only helps you to detect, not to solve the conflict. Now let's talk about latency. Latency. So the definition of latency is the time interval between the moment you send the request and the moment you receive the response. And the latency is composed of, first, the network delay, right? Router switch delay. The OS delay we can neglect. And the time to process your query. It can be the time taken to read data from disk or to compute something. And if we look at the physics of speed of light, we know that there is a physical limit, physical speed, above which you cannot go. So in fiber optic cables, you cannot go faster than approximately 2,100 kilometers per second. So it means that if you do a ping between London and New York, it will take minimum 56 milliseconds. You cannot go below this value. It is just physics, right? So let me ask you a question. If some database vendor says the average latency of my database is below 10 milliseconds, who thinks it is true? Raise your hand. Who thinks it is wrong? Raise your hand. Well, the answer is it can be true and wrong. Why? It depends on where you measure your latency, right? If you are just taking the measure next to the machine, it can be true. If you are taking the measure at the other side of the earth, it's completely wrong. So be careful when someone tells you some benchmark or some figures, ask the people, how do you take this figure, right? How do you measure your average latency? Now let's talk about failure. So in the literature, we have some definition of failure. Byzantine failure means you give an input and the output is incorrect. The value of the output is incorrect because maybe you have some bugs in your application. You can have performance failure. It is very simple. You expect the response to arrive, but it arrives too late. It takes too long. Omission failure is just a special case of performance failure. In this case, the response never arrives, at least never arrives within the timeout you define as a developer. And of course, the last category of failure, which is crash failure, is very simple to explain. Right? So in fact, in reality, what is interesting for us developers is only two types of failures: value failure and timing failure. And in fact, in distributed system, we are more interested by the timing issues. Right? Now, what are the root causes of failures? We can have failures because of hardware. Your disk just crashed. Your CPU is dead. You can have software issue, packet loss on the network. You can have some workload-specific failure. For example, if you try to flush a huge file on the SAN, and someone else is doing a huge read on the same SAN, so it can be blocked for a long time. Sometimes you can have failure related to your technology. If you are using a Java and JVM, you can have a garbage collection that lasts for 10 seconds, maybe more, right? And then during these 10 seconds, or I don't know, 1 minute, in the worst case, the server is just frozen. It doesn't reply to your ping. So from the point of view of the client, the server fails. And in fact, it's not that easy to define failure because in distributed system, we don't know which one of those causes happen on the server side. So we just assume that it fails. And in fact, the common definition of failure is a server fails is when I send a message, I send a request, and I didn't receive an answer within a time bound, which is called a timeout. Okay. So this is the usual meaning of failure. So we talk about failure, time, ordering. Now, how can we detect failure? Because first, it's already hard to define exactly, but how can we detect them? We have some known algorithms. The first one, the most basic, is heartbeat. You send a ping, you don't get a reply, it fails. You send another ping, you get a reply, it's up again, down, up, down, up. But it is too simplistic, right? So sometimes people use exponential backoff with threshold. What does it mean? You send a ping, you don't have a reply, you wait a little bit, for example, a few milliseconds, you send another ping, and every time the waiting time will increase exponentially until you reach a threshold, and then you say that this machine has failed. We have even more complex failure algorithm, failure detector algorithm, the fee-across detector, which is using advanced statistics to qualify if a machine has some probability to fail or not fail. Now, we said that time is not reliable. Global ordering is hard, and failure is hard to detect. So how can we achieve consensus? How can different machines agree on a single value in a distributed system? To be able to do that, we need to define some protocol, some algorithm. And all of those protocols need to validate the three properties below. First, validity. Some process have to propose a value to be agreed on. Second, termination. It means that after some finite time, the algorithm should finish and should propose a value. And last, property agreement. The proposed value should be the same for everyone. You cannot have a situation where some machines propose value A and some other machine propose value B, right? And the result cannot be A or B. It is A. The result cannot be A and B. It should be either A or B exclusively. So let's see all the algorithms we have for distributed consensus. So first we have originally two-phase commit. Two-phase commit is very well known for people working in relational database, but it has an issue, which is the termination issue. If the coordinator which control the algorithm fails, your two-phase commit will never finish, right? So the property termination is violated. So people devise three-phases commit. So it works except when you have network partition. Because if you have network partition, one of the coordinator will still handle some ongoing transaction, and there is another coordinator elected from the other side of the partition. So when the partition is gone, you may have inconsistent state. So the agreement property is violated. And last, to solve all this issue in distributed system, people have found the Paxos algorithm, the RAF algorithm, and the ZAP algorithm. So I will not, again, not go into the details. All those three algorithms satisfy the three requirements, and they all work on the idea of quorum. It means that for those algorithms to work, you have you need to have the majority of your machine alive, a strict majority. This is the end of the first part. So I give you a lots of ideas that we will apply on the next chapters. So now let's talk about data sharding and replication in distributed system. Data sharding. Why should we shard data? The first reason is for scalability. Right? You cannot put an infinite amount of data on a single machine, so you need to spread them. The second idea is to divide and conquer. So in fact, the state of a database, in general, can be represented at a smaller scale in a shard. How to shard? You have many algorithms. The first idea is the developer will provide the sharding algorithm and the target columns on which he would apply this sharding algorithm. You have another class of technology where the sharding algorithm is fixed. You don't choose it. You only choose on which column to apply this algorithm. So here are simple examples. Imagine that I have an user table. My sharding key is user ID. I shard by user ID. And my sharding algorithm is MD5. I take the hash of my user ID. So of course, those are my 5 shards, 0 to 19, 20 to 39, and so on until 100. I have 5 shards. So I have a kind of balanced distribution of my data. Now if I choose my sharding key as an email address, and the sharding algorithm is, oh, let's just take the first letter of my email address. You can see that the data distribution is completely unbalanced because people having their email address starting with Y and Z, there are very few of them, right? But the advantage now is I have an order, my shards are ordered, A to D, yes, E to H, and so on. Whereas with the hash sharding, this is not ordered by user ID. This is ordered by the hash value, which is not really usable. There is some other algorithm, like normal tree, which guarantee a balanced distribution of your data. So you can choose user ID or whatever sharding key. This algorithm will guarantee a balanced distribution of your data with some prerequisites. So let me ask you a question. Is it true or wrong? Who thinks it is true? Nobody? Who thinks it is wrong? And why is it wrong? Yes, thank you. Statistics. Statistics. It is not, in fact, it is not completely wrong. It is not always true. It's really different. So let me show you some games. So, of course, it is not completely true. You all know this game, right? Rolling dice. Imagine you roll your dice 100 times. This is a distribution of probability. There is no guarantee that you have the equal distribution. You roll them 1,000 times, 1,000,000 times. So it's the same for your hash sharding. The more you have data, the more you have distinct sharding key values, and the more the distribution will be balanced. It's all about statistics. There is no magic, right? So people should be really careful about this. If you don't, so this statistics things is really important, and you need to pay attention when you choose your sharding key. If I choose my sharding key as user ID, and I know that I have 1,000,000 users in my database, I'm fine. If I choose my sharding key as country, I have maximum 200 and something country in the world. So I have no guarantee that my user data will be well balanced. Now, what are the trade-offs of my sharding algorithm? When you have logical sharding, which allow ordering of your sharding key, it can lead to hotspot, as we can see, and imbalance of data distribution, but it allows range query. Right? Give me all the user where their email address start from first letter is start from A to B. This kind of inequality query can be done because your sharding is respecting the ordering of your sharding key. With the hash-based sharding, you lose this ability to do range query. You have only point query. Right? And some category of NoSQL solution, for some of them, they choose to have range query. For example, if you have a key value data store, if you restrict people to only look the value by key, exact key value, it's too restrictive. So they have to propose range query. In this case, they may have hotspot, right? So the solution for this kind of hotspot is rebalancing. So what does it mean, rebalancing? It means that sometime you move your data between the shard so that the amount of data per shard remain the same. So sometimes the rebalancing is automatic. Sometimes it is a manual admin process. But in any case, you should be aware of the fact that it is resource intensive because you need to read the data out of your disk into memory, stream them on the network, right? Any question about data distribution and rebalancing? Should we move on? Okay, move on. Data replication now. So we explain how can we distribute our data. Now how can we replicate our data? Easy, by having copies, multiple copies or replicas. You have two types of replicas, in fact. You have symmetric replicas, which means that each replica is exactly similar to others. And you have asymmetric replicas, master-slave style. It means that you have a primary replica, primary shard, which receive all operation write and read, and you have slave shard or secondary shards. Right. With symmetric replicas, all the write operation are just dispatched in parallel to any replica because there is no master, no role. And when you are reading, you can read from any of them. You can read from one of them, from two of them, from all three of them. It's your choice. With asymmetric replicas, when you write, your write should go first through the master, then the master will dispatch later the write to all the replica. For reading, same thing. The master can read from 1, 2, or 3 replica before returning the value to the client. And of course, the master also reads its own value, right? Because the master is the source of truth. But with this style of architecture, you have, of course, the bottleneck. So sometimes people, to avoid this bottleneck, some people will say, okay, we allow you to read directly the value from one of the replica without going through the master. It is possible. But then you open the door for inconsistency. So let me show you all the failure scenarios. First scenario of failure. Message loss. The master sent the insert to the replica. The message is lost on the network. So the replica never receive. So the replica will never give back an acknowledgement. So for the master, this is KO. It fails. Okay. Second failure. The replica received the write, but it can just drop the write because it is overloaded. Imagine that you have a long GC post. the insert is dropped. For the master, the replicas has failed. Okay. Last scenario. The replica has received the write, but didn't have time to send the acknowledgement back and then just crash. In this case also, from the master point of view, the replica has failed. So those failures are quite common. People all know them. Now there are some tricky scenarios. The first tricky scenario is the replica has received the write, is sending the acknowledgement, but the acknowledgement is lost in the network. It's rare, but it can happen. So from the point of view of the master, it has failed. It doesn't receive the acknowledgement. But still, your data is already written, right? So if you, from the client, if your client is reading directly from this replica, it will see the value. Although the master said the write has failed. Another scenario tricky is sometimes people, for performance reason, instead of writing the value directly to disk, they buffer them on memory to reduce the latency. So the replica just put the value in memory, send back the acknowledgement. So the master said, okay, it is written. But then the replica just crashed before flushing to disk. It means that the value written in memory is lost forever for this replica. So from the point of view of master, it has succeeded. But when you read directly from this, the value is no longer there. So again, it is another tricky scenario. So you should be aware of all of those tricky scenarios, and you should know what are the guarantees brought to you by the technology. What happened? Ask them, what happened in this scenario? What will you do? Do we have any mechanism to ensure the resynchronization of your data? And so on. CAP theorem. Any questions so far for this part? Yes.
Oh, I had a question. What are the pitfalls of the symmetric or synchronous replication?
The symmetric one? This one? What are the drawbacks, right? We will see it later. There are drawbacks, of course. There is no magic, right? I have seen another question in the background. Okay, no question. Okay. CAP theorem. So it was a conjecture from real world that has been formalized later in a paper. The CAP theorem say that you cannot have more than 2 out of 3 of those properties in any distributed system. Consistency means equivalent to have a single up-to-date copy of the data, high availability of that data for update, and tolerance to network partition, CAP. So usually people write this triangle, availability, consistency, partition, tolerance, and try to sort all the NoSQL database, data store on one of the 3 sides of the triangle. For example, if some database claim to be available and consistent, available and partition tolerant, or consistent and partition tolerant, and so on. But in fact, you cannot choose not to be partition tolerant in absolute, right? Because partition does happen. And in fact, the choice is not that binary. For example, our database, which belongs to the family AP, so they give up on consistency by default. They try to get more consistency by giving up on availability and so on. And all the family of CP, so consistent and partition tolerant, try to give up on consistency to get a little bit more of availability. So everyone on this diagram want to have all of those three, in fact. So the idea to know is, in the absence of partition, you can choose to tend towards C and A, consistent and available. But when the partition occurs, you need to fall back to either C or A. And the difficulty is the when. Again, as I said, it's hard to detect failure, right? So you have some time windows. You are not sure that there is a partition or not, and then you need to wait for a little bit. So all the details, all the devil is in the details. And for the family of A and P, available and partition tolerant, to get more consistency, they define what we call tunable consistency. It means that you can choose your level of consistency depending on your requirements. So what is consistency? That's the question. And in fact, in the literature, there are so many definitions of consistency. So many. And on my diagram, I just listed some of them, not all of them. So all the consistency levels on the bottom don't require coordination, don't require consensus. All of those in the upper diagram requires some coordination. It means that you need to have a lock or to use a Paxos or Raft or Zookeeper to achieve those levels of consistency. So, for example, some database claim to be CP, so consistent and partition tolerant, and when people test them, well, in fact, it's not really true. They support only read uncommitted, monotonic write, and write followed by read. So even if they claim to be something, you have to test by yourself. You cannot trust the marketing material. I can take an example of something I know very well, Cassandra. For example, in Cassandra, you can choose consistency level 1. It corresponds to read committed. It doesn't need any lock or coordination. You choose consistency level quorum. It corresponds to read your write, again without coordination. But if you use their feature that they call lightweight transaction, which is on the top part here, it means that it requires coordination. And in fact, in the background, this lightweight transaction is using Paxos, the algorithm, to achieve consensus. So it has a cost, of course. So when people tell you, oh, you should use lightweight transaction in Cassandra, for example, beware, be careful. You have to pay for this. This is not free. Now, what's about availability, the A in the CAP theorem? So is it the ability to read in case of failure, to write in case of failure? In the formal definition, it is only the availability for update, so from write. But in fact, from the practical point of view, if you cannot read, it is not really useful, right? And some real-world example, again, Cassandra claims to be highly available because it is an AP. Is it true? Some marketing material slide even claim to be continuously available. 100%, is it possible? So let's see. I have a cluster of A machines, and the nodes that are in orange are 3 of my copies, 3 copies of my data. I try to read with consistency level 1, and I have a network partition here. If I'm reading here, I'm lucky because I have at least 1 copy left to guarantee my read, consistency level 1. But if I am unlucky, and all of the 3 copies stay from this side of the partition, well, I can no longer read this piece of data, of course. So how can the marketing slide claim Cassandra to be continuously available? In fact, it is not related to the CAP theorem. It is not because it is an AP database. It is just because multi-data center. The fact that you can switch your client, if you read from this side of the partition and you don't get the answer and you get timeout, the client will just switch to another data center to get the data. So, and only in this scenario, you can have continuous availability. And even this is just theoretical, because of course, I can have the same kind of partition here in my other data center. But in fact, the probability to have at the same time the exact same kind of partition, network partition, is quite rare, in fact. But when people say that when Cassandra has continuous availability, it is only possible if you have more than one data center. So be careful with the marketing slide. Now we finish with the last part, a comparison between master-slave and masterless and all the advantages and drawbacks. So the pure master-slave architecture, a single machine for all write and all read. The advantage is, of course, because every operation goes through the same machine, you can have ordering, right? Operation can be serialized. It is easy to think about, and you can perform pre-aggregation. What I mean by pre-aggregation is you can pre-compute the sum, the average, the mean, the max of some of your value. Because you have a single master, which is the source of truth. The drawbacks are, of course, you cannot scale on write. Maybe you can scale on read, but you may have consistency problem, as I showed before. And of course, you have a single point of failure. So this is the diagram of a master-slave architecture. So to improve, to get rid of this big single point of failure, people say, now let's use the divide and conquer strategy. I shard my data, and on each shard, I have a master or primary shard, primary replica, and then secondary replica, but it's the same thing. Call it master-slave or whatever you wish. It's the same idea, right? So now, the advantage is your operation can still be serialized, ordered in a single shard. You no longer have the big single point of failure anymore. But the drawback is now you can no longer have consistency, global ordering, I mean, that cross different shards, unless you have a global lock again. And you lose your ability to do a global pre-aggregation. You can only pre-aggregate on a single shard. Sometimes people say, okay, you can read in some marketing materials, failure of a shard master is not a problem because it takes less than 10 milliseconds to elect a slave into a master. So it may be true, it may be wrong. In fact, the question is not how long does it take to elect a new master. The question is how long does it take to detect a failure. Again, I come back with my failure detection. And to detect that a node has failed, sometimes you need to reach a timeout, right? And timeout is defined in terms of seconds and not milliseconds. So what is important is you spend like 5 or 10 seconds until the timeout is reached. And once the timeout is reached, you said this machine is offline. And then you will elect a new master. But during this time interval, you cannot operate for write, right? So what is important is not how long it takes to elect a new master, but how long it takes to detect a master is down. We have also a family of technology that I call the fake masterless or fake share nothing. So last year, I have read some documentation, official one, in the internet. They claim to be truly masterless, and in the same website, you have this. Truly masterless, and then master node election. I say, what happened there, guys? There is a problem with your documentation. And they say, oh, no problem. We will update our documentation. No problem. So it was back last December. And This month, I just check again the documentation. So yes, they removed this master node election completely, disappear from the website. They said still it is a masterless architecture, okay, no problem. And then I click on this technical overview. Oh, what does it say? So when you write, first the write is routed to the primary shard, executed on the primary shard, and when it is successful on the primary shard, it will be executed on all the shards. Remember this?
There is no master. No master word.
Yeah, there is no master word. Yeah, they remove the master, copy and paste, replace. But it's still the same idea, right? So be very careful when people say, oh, share nothing, or when you see the primary shard or primary something, there is some notion of master central state. And whenever you have central state, you have trade-off. Of course, there is no free lunch. So now let's talk about the weaknesses of and the advantages of masterless architecture. So of course, the advantages we all know, no master. So you don't have this master going down. But now the problem is how can you manage consistency, right? How can you know which copy of your data has the right value? Because there is no master to decide. So we can have some data structure to help vector clock to detect inconsistency or CRDT. I will not go into detail of CRDT here. If you are interested, you can read the paper. You have also the notion of coordinator in masterless architecture. The coordinator is the machine which receives your write and just dispatch your write to the correct copies. It is just a network proxy. But if you ask yourself, what happens if this coordinator dies? And in fact, in those kind of architecture, anyone can be a coordinator. Right? It is a symmetric role that can be taken by any machines. So losing a machine is not a problem. You lose, this operation will fail, but the next operation will continue to work. Right? CRDT. So React, which is a masterless database, implement a lot of CRDT structure, register, counter, set, and maps. Cassandra only implement the last write-win register, which is based on timestamp. It means that every time you write a value in Cassandra, you assign a timestamp. And if you have two different values for the same column, the value with the biggest timestamp will win. But we said that timestamp is not reliable, right? Of course, you can have issue with that. So let me show you, because we are running out of time, let me show you some example. You update some age of user 1 to 32. The update is routed to this coordinator. It has its local time. So the coordinator will assign this local time, 10 o'clock, 1 second, 50 milliseconds, to all of the copies of the data with this timestamp. Now someone else later update this age to 33. But you are unlucky. On this coordinator, the time is not synchronized correctly, or exactly the same. And the time is in the past, like 20 milliseconds. So now your new value is written with a timestamp which is in the past. So when you are reading, you are doing a select. Cassandra will return you 32 and not 33 because of timestamp drift. Right? So this is a real issue. And this is one of the biggest weaknesses of Cassandra, because there is no master to guarantee which one has the true value. Right? So to solve this issue, in fact, functionally, it's quite rare that you have multiple clients updating the same value on the same column of the same row. Or if you want absolute guarantee, you can use like wait transaction to have this conditional update. But again, Nothing is free. If you use this lightweight transaction, you pay the price of 4 network round trips, which is extremely expensive. Right? Summary of Masterless: no single point of failure, no failover. Drawbacks is it's really hard to reason about, and you lose the ability to pre-aggregate again. How can I have a min or a max if every time I need to read the value from 3 different replicas? I cannot pre-compute some min-max. Impossible. And that's it. Any question? No. Thank you.